Hello and welcome. From the European Space Operations Center in Darmstadt, Germany, this is Space. We are getting closer than ever to understanding the origins of the universe. For the first time, we have peeked behind the veil that covers the Big Bang. So, what do we really understand about the beginning of everything? We'll find out in this program. But first, some other news from the universe this month.
Astronomers have discovered an exoplanet located oddly far from its star in the constellation Pisces. It takes 80,000 Earth years for the planet to complete one orbit around its sun. Venus Express readies to enter the atmosphere of our neighbouring planet. The aerobraking experiment will complete the European spacecraft's mission after 8 productive years orbiting Venus.
For more science news, follow us on social media. And now the latest on the Big Bang.
A shockwave hit the foundations of cosmology recently with the announcement that the background imaging of cosmic extragalactic polarisation BICEP-2 experiment at the South Pole had spotted the footprints of something called primordial gravitational waves. These waves may be a sign that a theory known as cosmic inflation can be confirmed.
BICEP-2 have found a signature of primordial gravitational waves. To me, this is one of the big unanswered questions of all of science. Did inflation happen? And if inflation really did happen, do the gravitational waves exist from that? And it looks like the answer is yes.
Einstein believed that gravitational waves, a kind of ripple in space-time, did exist. The findings at the South Pole appear to confirm his theory. The big announcement came just months ahead of this autumn's release of polarisation data from the European Space Agency's Planck satellite.
The BICEP-2 announcement was quite surprising, not only to the Planck teams, but to the whole working field. Surprising because of the high strength of the signal that they found.
The question now is whether the gravitational wave signal really did come from the dramatic first moments of the universe, the period known as inflation, or did they come from interferences such as galactic dust?
Of course, every experiment wants to be first, and in that sense it was a little bit of a disappointment, because if, again, with an if on it, if the BICEP measurement turns out to be correct, then we should have been able to measure it and come out with that discovery first. I said if because there are still some significant question marks about the BICEP measurement, which need to be answered.
The reason for the excitement is that gravitational waves could teach us a lot about the universe. At the European Gravitational Observatory near Pisa, scientists are trying to detect those waves.
We are here near to the tunnel that is long 3 kilometers. We have here 2 tunnels, perpendicular one to the other. In each of them there is a light beam that goes from the central building to the end tower, where the light is reflected and goes back to the central building. The aim of this very large infrastructure is to detect gravitational wave.
In theory, a wave passing through the Earth would stretch the tunnels, changing the time the light needs to make a round trip between the mirrors, and that can be detected.
This is the core of the detector. It is the place where the 2 laser beams recombines, and they are detected exactly down there. So it is the place where we really see if a gravitational wave has hit our detector. It is not something that big. In fact, the level of stretching is very, very tiny. It's about 1,000th of the size of a proton.
Studying the universe with gravitational waves can bring about a wealth of new data. Produced mostly by catastrophic events like collisions of black holes, these waves are completely different in their nature from electromagnetic radiation.
The frequencies of the coalescences of compact stars fall within the domain of audio frequency. That's to say, we can hear them. When we detect and record these signals, we can listen to them.
This is a simulation of how a gravitational wave would sound if converted to audio. But to capture this vibration, the mirrors of the observatory have to hang perfectly still. On our dynamic Earth, that's not always easy to achieve.
We're trying to detect movement in space, not on planet Earth, so we absolutely must isolate every part from the ground.
We are fighting against thermal fluctuation with our seismic noise. Obviously, we are fighting also against trucks or railways. It's a typical task of a director.
Of course, launching experiments into space is one way to avoid Earth's noisy environment. ESA's LISA mission set for launch in 20 years will have its mirrors wide apart in order to improve the sensitivity of measurements.
LISA stands for the Laser Interferometer Space Antenna, and it's a constellation of 3 satellites, and they're separated by about 1 million kilometers. And we measure the distance between 2 of the arms, very similar to the ground-based, and by comparing the lengths of the arms, we've measured the gravitational wave signal.
The trio of satellites linked by a precisely aligned laser beam will follow the Earth at a calculated distance to balance out the gravitational forces.
When LISA is launched and operating, it will be the largest man-made thing ever, in the sense that the 1 million kilometers is about something like 2.5 times the distance to the moon as a separation of the satellites. And we measure the relative difference between the satellites to a few picometers. So that's about 1/100th the size of an atom over the 1 million kilometers.
A Pathfinder mission aims to prove the concept next year, and a full-scale LISA observatory is planned for 2034. Then we'll hear the cosmic symphony from neutron stars back to the Big Bang.
Every time people have trained their instruments on the sky, they've learned things that were completely useless to begin with, but which advance scientific knowledge. And science is useful. Understanding how our universe works means we can do things.
Can we use gravitational waves to understand the very earliest part of the universe? This remains one of the great questions, and this is the reason why primordial gravitational waves are so exciting in science.
This summer, the Rosetta spacecraft will aim to orbit a comet and then put a lander on its surface. The comet hunting team here in Darmstadt are at the controls.
Previously on Comet Hunters, we've watched Rosetta getting ready for the crucial part of her cosmic journey.
It's a very important phase because we started a few days ago to do the maneuvers that we need to get close to the comet.
This is a key moment. Either it works or it doesn't work.
The coming months are going to be much busier. We will have to start flying around the comet. Nobody's done that before, so while we're doing, we have to learn how to fly.
Timing will be tighter and tighter, so a good teamwork is fundamental for the success. Dear Rosetta, I hope you appreciated the way I took care of you in the past years, and I wish you all the best for the coming months.
Take it easy, it's gonna be another few weeks of maneuvering. Don't shake, do it calm, and it will be over soon.
That's it for now. Next month, we'll get inside your TV and find out how the world watches the World Cup. See you then.